Hello students. In this one, we will be discussing work, energy, and power. So unfortunately, we didn't have like an interactive lesson today. However, I think if you watch the whole entire video, there will be a lot of things you will learn in this video, of course. So now we are looking at work, energy, and power. So obviously, we need to understand some of the concepts on this topic, like the likes of what is work. So work is done on an object by a constant force. So what this means is that for us to have work done in an object, there must be a force, and this force must be constant, right? So it's basically the product of the magnitude of the force. So what work done is, it is the product of the magnitude of the force and the magnitude of the displacement and the angle between the force and the displacement, right? So I think if you look at the definition there, sometimes you would think it doesn't make much of sense. But if you look at the formula, you will see that we are talking about the constant force. So this here, it's this constant force that we are talking about. And then the delta x, it is the displacement. We are looking at the displacement of the force. So let's take for the displacement of an object. So let's take, for instance, this is our object here. We apply a force of 50 newtons to this object, and then the object now gets displaced for let's say 30 meters. So now if that is the case, now we check here on our diagram. Let's say now we also have the frictional force. The frictional force, we can say now it's 20 newtons. And then we have another force going down. Say the object's mass, it's 2 kg block. It's a 2 kg block. So the 2 kg block is being pulled to the right. You can have a picture here. So this 2 kg block is being pulled to the right with the 50 newtons force, and then the frictional force in the situation was just 20 newtons. And now what is the gravitational force? The gravitational force is the object's mass times the gravity. The object's mass is 2 kg times the 9.8. So now what is this? This is 9,8. 2 times 9,8. 2 times 9,8 will give you 19.6 newtons, right? And then now the normal force, it's the same, right? So the normal force is the same as the gravitational force in this situation here, right? So if we are asked to calculate the work done, by each force, that is the starting point. We need to look at the work that is done by each force. So taking a look at the work done by each force now, you will notice that the work done by the likes of the F force, it's going to be the force, constant force, times the delta x and the cosine. So here we must multiply the cosine of the angle, theta. So by the way, people, the theta, it is just the angle. Theta is an angle between, so it's between the force and the displacement. Between the force and the displacement. So now what you will notice there is that For example, if we look at this scenario here, where we have our 2 kg block being pulled to the right by a 50 Newton force, you will notice that we are going to have work done, and this work that is done to this object, it is going to be done by the force F and done by all the other forces. So all these forces are doing work on the object. We just don't know the magnitude of the work that is being done. So if we have to calculate the work done by each force here, and then we start with the force of F, you will notice that the work done by force F, it's going to be 50 newtons. That 50 newtons the force. We substitute in the force. So now, what is the delta x? The delta x here, it is the displacement. So the object was displaced from this point A to point B here, and then now you can see that now the object is at point B. What is the displacement? The displacement is 30 in the situation, and then we say cos. Now the theta. With regards to the theta, we are looking at the angle theta, and the angle theta, it is the angle between this is the force F, which is the 50 newtons force. So you'll notice that here the force and the displacement are in the same direction. So the object is being displaced from A to B. So by the looks of things here, the force and displacement are going in the same direction. So if the force and the displacement, the angle theta, which is the angle between the force and the displacement, it's going to be 0 degrees. So it is always the case that if the force is going exactly in the same direction as the displacement, we are going to have the angle theta as 0. So you're just going to put 0 degrees there, and then now after that you punch the things on the calculator. If you punch on the calculator, it's going to be 50 times 30 and then cos 0 degrees, right? Now you will have that the work done on this object by the force F, it is going to be 1,500 newtons, right? It's going to be 1,500 newtons. And then now we can move on to the work done. So this one here is the work done by the force F. So work done by the force F. So now we can calculate the work done by frictional force. So let's calculate the work done by frictional force. So the work done by frictional force here is going to be the frictional force delta x cos theta. Now, what is going to happen in this situation is that, remember, the object is moving to the right, and when the object is moving to the right here, the frictional force always opposes the motion. So the work done by the frictional force, it's going to be, you're going to substitute the frictional force. What is the frictional force? Is 20 newtons, right? FF. And then the delta x, it's going to be your displacement, which is still 30. So the displacement is the same, right? However, the angle is going to be different, right? The angle is going to be different. So now let's go and investigate the angle. Looking at the force, this force, which is the frictional force, is going to the opposite direction of the motion, and it's going to the left. However, the displacement, which is from A to B, it's going to the right, the delta x. So now we'll notice that here, the angle between them, it's going to be 180. So the theta, if the force and the displacement, they're going in opposite direction, you can see that the force is going to the left and the displacement is going to the right, then it's always the case that the theta, it's going to be 180. So theta is 180. You're going to put your theta as 180 for the for the forces that are opposing the displacement. Now it's going to be 20 times 30, and then you cosine 180. The answer is going to be negative 6 100. Sorry people, the SI units for the thing, it's supposed to be joules, right? It's supposed to be joules and not newtons, right? Very sorry about that, people. So it's, instead of newtons, we just put joules, right? That is the correct SI units for the work done. So the work done, it is not like a force, it is joules, the SI units, right? So I'm noticing now that we have to just write joules. And then good. Now the work done by the other forces that are acting there, the likes of forces like the normal forces, you will notice that okay, let's calculate the work done by gravity first. Let's calculate the work done by gravity. So the work done by gravity here, it's going to be the gravitational force delta x cos theta. So always when you're calculating the work done by the force, you can calculate it from taking the force and multiply the delta x, which is the displacement of the object between those 2 points, and then you look at it, right? So now here we are going to take the mass, the object's mass, right? What is the object's mass? You remember Fg is equal to mg. So object's mass is going to be 2 kg here in the situation, and 9.8 is the g. It is the g, so Fg, we have it there, and then delta x, it's going to be 30 because the object is being displaced 30 meters to the right. And then now we'll cosine the theta. Theta, it is the angle between the force and the displacement. Looking at this one, the gravitational force is going exactly downwards, and the displacement in the situation, which is your A to B, it is going to the right. But then you will notice that the angle between the force and the displacement in this situation is 90. So the theta in the situation is 90 degrees, right? So when the theta is 90 degrees, you will notice that when you look for your work done by the gravity, work done by force of gravity, it is going to give you 0 joules, right? So it's going to be 0 joules. And then now it means that if the force is perpendicular, if the force is perpendicular to the displacement, like in the situation here, and also with the situation of the normal force, if you notice here that the normal force also, if you take its force and then delta x cos theta, you will notice that the normal force is going upwards. Notice that the normal force is going upwards. Then if the normal force is going upwards, the displacement is going to the right. And then now, what is the angle between the force and the displacement? The angle between the force and the displacement in the situation, since the two quantities are perpendicular to one another, we will have that the theta is also 90. So all the time, people, when your force is perpendicular to the displacement, when your force is perpendicular to your displacement, we are going to have the theta as 90 degrees, meaning that the work done by such forces that are perpendicular to the displacement, we are going to just have 0 joules. So sometimes you don't even have to bother calculating the work done by those forces, because it is going to be 0 in all the cases, right? So normal force is always perpendicular to the surface, and the normal force will forever be perpendicular to the displacement of the object, because the objects that will be displaced will be either on the horizontal plane, and you can see that your normal force will be perpendicular, and then if it's on the surface that looks like this, it's still perpendicular to the displacement. So you can either go up or down. The object can either go to the right or to the left, so meaning that the normal force will always do 0 amount of work to these objects. However, the gravitational force will only do zero amount of work for objects that are on the horizontal surface. So all the objects on the horizontal surface, the work done by gravity in the situation, it's going to be zero. However, it is not going to be the case with the ones that are going on this direction, which will be discussed. You can see that it's not perpendicular, but it's just at some angle there, right? And then you can bring in components for your work done by perpendicular. I think you can bring in component in there, the components of gravity, especially if we looked at mechanics, right? Look at the forces that are acting on the object, right? Something that we're going to do, of course, as time goes. But just keep in mind that the work done by gravity, it is only going to be zero when the surface is horizontal, but not on an inclined plane. So people think we are moving there. We looked at the work, then I think we looked at the work done that was done. So we looked at the work that was done to the object by different forces, right? The first force that we looked at the work done for was the force F, and then the other one was frictional force. The other one was number 3 there, which was the work gravity. Then the number 4 one, which was just obvious that it is going to be zero in all the cases because the object will always have a perpendicular normal force to the displacement, right? Good. So now if I ask you now in this situation to calculate the network that was done, what is the network that was done? The network, normally we add all the work that is done or that was done by all these forces, right? So all the contributions, some of the contributions are negative and some of the contributions are positive. We add everything and some of them are zero, right? So it means that it will just contribute zero. So now we add all the forces, we add all the works that are done by the forces. And now the first force that did work in the situation was the force F, which was the applied force. Remember, the situation was this one here, the scenario. Force F was 50 newtons. So now we're going to substitute in the work done by that force, and the work done by that force is going to be 1,500 newtons. So 1,500 joules. So it's going to be 1,500 joules. Plus, we look at that other one there, it's having a negative work, right? So let's go back to the definition here. By definition, they said that we have a positive work. So what is positive work? Positive work means that the kinetic energy of the object, it's going to increase. And then for negative work, we will notice that the kinetic energy of the object, it decreases, right? So in this situation, if a force is doing positive work, like the likes of this force here, we calculated and saw that it's doing positive work. This one is doing positive work, and this one is doing negative work. This one increases the kinetic energy. So this one here, it increases the kinetic energy of the object, and this decreases the kinetic energy of the object. Remember, kinetic energy is related to how fast the object is moving. So the object will only move faster if we have a greater force that is doing positive work. But if we have a smaller force that is doing positive work, the object will obviously decrease. Or if we're having a negative work done, the object will decrease its kinetic energy, right? So now the negative work is normally done by forces that are opposing the motion, right? Forces that are opposing motion, they will do negative work. Forces that are going in the same direction as the motion will obviously do positive work, those that are perpendicular will do 0 amount of work. So I think it's perfectly fine there. I think it's clear to everyone. So now let's add all our forces here. Let's add all the works done by the forces. So this one is going to be negative 600 joules. And then the work done by gravity in the situation was 0 joules. And then the work done by the normal was also 0 joules. So what is the net work done here by all the forces that are acting on the object? It's going to be 1.5 plus negative 600 plus 0 plus 0, and now the answer is 900 joules. So this is the net work done by all the forces, right? So remember what network is. Network is basically the work, the sum of the works that are being done by the contributions of all the work done, all those forces, right? But if you take a look at this one here, we have something called the work energy. So the work energy theorem, it tells you that the net work done on an object is equal to the change in kinetic, so in the object's kinetic energy, right? So the net work done on an object is equal to the change in the object's kinetic energy. Or you can simply talk about the work done on an object by the net force is equal to the change in the kinetic energy of the object. So what does that statement over there mean? It means that the net work done, this network can be done by the net force. So if you know your mechanics very well, you know your forces acting on the object, you can find this F net for us. Find this F net for us and then plug it in there, right? Remember, F net is equal to ma. So if we have the object's mass and the acceleration, we can get the net force of that particular situation. And then now the work net done, according to this thing, it's telling us that the net work done is equal to the object's change in kinetic energy. Change in kinetic energy means that we are looking at the initial kinetic energy. Remember, half mvf squared minus half mvi squared, right? So the initial kinetic energy minus the final kinetic energy minus the initial kinetic energy over there, it's equal to this formula can help us to calculate the network. So the network can be calculated in 3 different ways, right? So we can calculate the network from this way, number 1 here, the one we have here, this one by calculating the work done by each of the forces acting on the object, or we can look at the sum of the forces, right, and look at the direction of the net force, where is it going, and then we can still get that, right? So I'm not sure if these values, because these values, if these values are going to be consistent with that other formula. So let's find the work net using the different formula, delta x cos theta. Not sure if it's gonna work, but you can try it there. You can try it. So I just want us to move on to this exam question here, maybe just to see if we can be able to apply what we've learned, and we can also discuss if it's something new, right? I think it's a very good question that we can use to learn this thing, right? So I'm just gonna erase this part here just to have enough space there. You can see that the work net on the previous one was 900 joules. So let's erase there. Now, on this question, we were given that it was question 12. So we're given that a slide PQR at an amusement park, it consists of a curved frictionless. So this thing, there's a section that is said to be frictionless, right? So I'm going to explain what you should keep in mind when you see that frictionless weight. It indicates something, right? So now let's look at the other one, PQ. That's the one frictionless, right? This part here is frictionless. Good. And a section QR is rough. So there's another one there that is rough. I think we can give it a different color. Maybe this one would do for a rough surface. That other surface there is rough. Other surface there is smooth, indicated in yellow there. So the other one is rough, the other one is frictionless, right? And a section QR, which is rough, straight, and inclined at an angle 30 degrees to the horizontal, right? So the starting point P is 3 meters above point Q, right? It's 3 meters above point Q. And then the straight section QR is 5 meters long, right? We are looking at the length there, people. We are looking at the length of that QR, which is the displacement of the object, right? So a learner with a mass of 50 kg. So this is much more practical. You can have a picture of this learner. We're saying that a learner is starting from rest. So if the learner is starting from rest, people, we know that we're having some information here, the initial velocity of that learner at whatever point, which is point P. So that learner's velocity at that point P there, it's going to be 0 meters per second. We have the velocity and we have some information there, right? So now the slide, okay, a learner with a mass of 50 kg starting from rest at point P slides down. So this learner was here. I'm not good at drawings, but you can see that this learner is here and then is going down there, right? It's smooth there. It's cruising nicely there. You can see him. You can see that learner. Don't know if it's she or he, but it's sliding down the PQ and then continues down the straight section QR, right? After that. So now you were supposed to state the conservation of mechanical energy. So this is grade 10, people. So the conservation of mechanical energy, you did this in grade 10. Maybe you forgot, but this is something that you must have done in grade 10. And if you go to grade 10 and look at energy, your energy notes, or you can look at grade 10 notes, you will notice that it's there. So how do we state it? We need to say that we need to talk about the total mechanical energy. So this states like the total mechanical energy in an isolated system. So I'm just going to write the total mechanical energy in an isolated system. Is conserved. So when I write this looks similar to one of the laws you know from momentum, the conservation of momentum, of linear momentum. So the total mechanical energy in an isolated system is conserved, right? Good. So now we can go to the second question now. So you know that what comes after this one, you know that there's going to be mechanical energy. Mechanical energy, what is mechanical energy? mechanical energy, it is the sum of the potential energy and the kinetic energy at a point, right? So now they're telling us that the mechanical energy at some point A is the same as the mechanical energy at some point B, right? So now EPA plus EKA should be equal to EPB, right? Potential energy. So this one is potential energy. So potential energy is mgh. And then this other one here is half mv squared, right? So I'm just writing the conservation of mechanical energy formula there. EKB, just like that. So now let's go on to 12.2. Now they wanted us to calculate the speed of the learner at Q. How do we calculate the speed of the learner at point Q? We are going to use the conservation of mechanical. So however, conservation of mechanical is very simple. We just say EMA. So what is our point, our initial point there? I think I can just say initial point. We can say our initial point is point P, which is supposed to be equal to the mechanical energy at point Q. So what is the mechanical energy at point Q? So here we'll add the kinetic energy. So let me just substitute the formula. So it's going to be mgh I plus half mv I squared. So this is for initial. So the initial potential energy plus the initial kinetic energy, which is going to be equal to the initial to the final potential energy and the final mechanical energy of this object. So you will notice that it's always for one object, this formula, right? We are dealing with one object. It's not like it's two objects. So the m there, everywhere where you see m is common. It's the object's mass, it's the learner's mass in the situation, right? So now what's going to happen there is that you will notice that initially he was there at point P, right? At point P, what is happening? What is the object's mass? Object's mass is 50. What is the G? G is 9.8. And after G being 9.8, what is the height at that point? Initially, if we substitute our height as 3 meters, we are saying that this one here, it's our zero reference. So if this is our zero reference, it means that the point at point Q will have 0, right? So this one, we add it with the velocity. It's saying that it's starting from rest, so it means that here it's going to be 50 and 0 squared. So at this point P there, he is at rest. You see that? The learner is at rest. Let me not say he. It could be that it could be the case that it's she. So but that learner is at rest. So now if you say equal sign here, what is the object's mass? Object's mass, it's 50 times 9.8. We will not have enough space there. Times 9.8. And then what is the height? The height final. So this one is our initial point and this is our final point. Our final point there, the height final is 0. However, the height initial is this height here, which is 3 meters, right? The final velocity is what we don't know, which is what they're actually looking for there, which is the final velocity is the same as the velocity at Q. So that's what we're looking for. So this one is going to be 0, right? And then plus half. What is the object's mass? 50. The velocity we don't know, but it's squared. And now we can calculate. So in the process of calculating this, I think we should we can simplify this part on the left. Let's simplify the part on the left there. When we add this part on the left, we will see that it's going to be 50 times 9,8 times 3. The answer will give us, if you use that one, it's going to give you 1470. For that. And on the right you'll get, I think this one will just give you 0, and then you'll get 0 plus half of this one. You're saying half of 50 is 25, so it's going to be 25 VF squared. You divide both sides by 25 people. Then when you divide both sides by 25, you get the VF squared is equal to, what is the answer? 58.8. So you introduce square root both sides because you want the velocity. So now the velocity final, which is at the point Q, it's going to be the square root of the answer we got, right? What is the square root of the answer? It's going to be 7,67. 7,67 meters per second. So that is the correct answer we got there for the velocity at that point. So this is 7.67. And people, please take this opportunity to also go and look at this conservation of mechanical energy, because it's going to help you, but it only applies on a smooth surface. So the surface should be smooth, or the surface should be frictionless. You can see how easy it is. It has got limitations. It can only be applied on a frictionless surface or a smooth surface, right? Okay, that's good. Now we can go down now, and I think you have it there. So just one space for the other question, the likes of question 12.3. So I will just erase there, so we can quickly take a screenshot of what you have here. But at least we have the velocity 7.67 meters per second at that point Q. Now we can quickly just erase here, just to create space. So let's erase here and create space for the next question. Now, on that question now, 12.3, they saying that the surface is rough, right? If you look at the surface there, I think the object is now moving in a different surface, and that surface looks more like this. It is a 30-degree surface, the inclined. So this point is point Q, this point is point R. The surface looks to be, it's said to be rough, and then here we can have our initial point, then here we can have our final point, right? What the displacement here, so the displacement in the situation, it's 5 meters, right? It's 5 meters there. The object is here, right? So now what's going to happen here is that we're going to have some force, like gravitational force going exactly downwards, and then the likes of forces like your normal force. So if we draw the free body diagram for 12.3, you will notice that we will have a force here, Fg, going exactly down, and then another force here, which is said to be the normal force. Do we have any applied force to the object? So they're saying that draw a labeled free body diagram for the learner while he or she. So it's clear that in the situation, in terms of gender, they just didn't want to specify. So you can see that now, since the object is going down, people, now is sliding down. The learner is sliding down. It's going down there. So now it means that the friction is going to oppose the motion. Friction will go up the incline since the learner is going down the slope, right? So now we are going to have the learner going down, and this is what we will have, right, for the free body diagram. Can we go to 1.2.4? So now we need to calculate the magnitude of the frictional force acting on the learner. So I think we missed something there. They'll say that the coefficient of kinetic, the mu k, between the learner and the surface, it's 0. So we're given the mu k, that is 0.08. Now we need to calculate the magnitude of the frictional force acting on the learner. So I think you know that when you look at your free body diagram there, you remember that the normal force here, so obviously this is what you would have drawn, right, for the free body diagram for 12.3. Here I just want to draw the free body diagram with all the components here, that we can clearly see what's going to happen here. So now when we have components here, we're going to have the components of gravity. We will have the likes of component, the perpendicular component here, and the parallel one, FG parallel. So we know that FG parallel is mg sine theta. This one g cos theta. So I think everyone knows that by now. So now we are going to calculate the work done by friction. It's going to be Fk mu Kn. So what is the Fk? Fk, it's going to be the mu k. It's going to be equal to mu k. The mu k is the value given, the 0.08. And then what is the normal force? The normal force in this situation here, you must see that it's an incline. So if it's an inclined plane, we will say that the normal force is equal to mg cos theta. So it's equal to mg cos theta. What is the object's mass? Object's mass, it's 50 kg. Remember, it's the mass of the learner, 50 kg times 9,8 times 9,8, and the cos of the angle of inclination, which is 30 degrees. Now we can calculate our correct value for the frictional force. It's going to be 0.08 times 50 times 9,8 times the cos of 30 degrees. You will get 33,95 newtons. That is the correct value there for the friction, because the friction, remember, it is just the mu k and the normal of the object. Obviously it's for objects that are on the surface, right? So now we can go to the 1.2.5. I'm not sure how much of the space we need for that question specifically, but just check there. That question is saying that you need to use the energy principles. Remember, we looked at this thing, right? And I think by now we know the energy principles, right? Fortunately, maybe we didn't look at all the energy principles there, like the likes of but I think we almost there, because we looked at this one. We have discussed about the positive and the negative work that has been done. And another work energy theorem, we've also looked at it. We also looked at the principle of conservation of mechanical energy. We just haven't looked at the conservative forces and the non-conservative forces. However, people, if we have to look at that one quickly, a force for which the work done, what is said by a conservative force is that it's a force for which the work done in moving an object between 2 points is independent. So I think people are there thinking it's going to be independent. The conservative one, it is the one that is independent. The conservative force, it is the force for which the work done in moving an object between 2 points is independent of the path taken. However, the non-conservative force, it is the one that depends. This one is a force for which the work done in moving an object between 2 points depends on the path that is taken. The likes of your frictional forces and your air resistance, your tension forces and your applied forces, those are going to be your non-conservative forces. Those are good examples for non-conservative forces. However, for conservative forces, in this work, energy, and power, we tend to focus only on the gravitational force, right? But don't be surprised if maybe they create a question that has elastic and electrostatic forces there, and then you have to do some nice calculations there. But mostly what I've seen in this one, mechanics, we tend to focus only on the gravitational force, right? Good. And then now the power, we can calculate the power done by the force by taking the work into consideration, the work that is done by that force. So power is the rate at which the work is done or energy is being transferred, or transferred or expended. But I think it's still fine there. You can still use the definition that the teacher gave you. So people, let's quickly go and calculate the. We can use any formula there to calculate that one, but I would like us to use the work energy theorem for this one. So the work net is equal to the change in the kinetic energy. So I want us to use the work energy theorem for this question. So now the work net done, now it's going to be work done by, we have how many forces? We have the normal force, we have the force of gravity, and we also have the work done by frictional force. So I think it was 3 forces there acting. You can see already that I said in class, I said that the normal force is going to be 0. Sorry, I said earlier that the normal force contributes 0 amount of work because it's perpendicular to the object. Then the work done by gravity is going to be the gravity delta x cos theta plus the work done by frictional force. The frictional force is going to be, do we have work done by frictional force? It's going to be the frictional force delta x cos theta as well. Then here we're going to have the change in kinetic energies EKF minus EKI. And now this is going to be half mvf squared minus half mv squared. So this is going to be 0. So the 0 goes away. And then the work done by gravity, let's go and investigate what it's going to be. So people, work done by gravity, this one Fg here, is always the case that the perpendicular component does 0 amount of work, right? The perpendicular component does 0 amount of work, right? So, okay, let's just say, let's not use component necessarily. We're just going to use the definition. So the definition of work done says you take the force. So what is this force here? It's going to be mg. So the force is mg, is the object's mass. Object's mass is 50 times 9,8. And then delta x, it's going to be 5 meters. So people, let's look at it. The delta x there, it is 5 meters, which is this displacement here. And the object's mass, it's going down. So the object's gravitational force is going down. What is this angle here? 30 degrees. Where is the object going, people? I think it's going down. If you look at it, the displacement is going down. It's not going up. It's going down. So now in this situation, if the object is going down, we get this angle here. We want to look at the angle between the force and the displacement. And the displacement is this one here. So the angle between the force and the displacement here, it's going to be this total. You can see that the total angle there is 90. So this one is going to be 90 minus 30. So if the object was going up the incline, it was going to be 90 plus 30. So that angle there would have been 90 plus 30. So you can just memorize that if the object is going up, so if object is going down, the theta for gravity, for work done by gravity, it is going to be 90 minus the angle of inclination. But if the object is going up, if it is going up, the theta is going to be 90 degrees plus 30 for the work done by gravity. So you're going to put your displacement there, and then when you come to your cos theta, you don't put the theta as 0 or 180, because the gravity is not going in the direction of the displacement, but it's going in some direction that is going exactly downwards. And you can see that your slope is in an incline. Then if the object is going down, then the angle is going to be 90 minus. So here you will say 90 degrees minus 30 degrees, and then plus what is Fk? The object's frictional force. So the frictional force that the object experiences, it was the one that we calculated is 33.95, and delta x is 5 meters. So it's going to be the cos of the angle theta. What is the angle theta there? The angle theta, people, it is the angle between the force and the displacement. Angle between the force and the displacement for gravity is 90 minus 30 because the object is going down. However, for friction, it's going to be the theta, it's going to be 180 because the object is going down and the frictional force is going up, is opposing the motion. You can agree with me on that one, that the angle is always the case, that for friction is always 180 degrees. Now, here we can have half. What were we supposed to calculate here, people? Okay, I just thought maybe we can see the question here. And they want the speed at r. The speed at this point r here, if this is our initial speed, this is our initial, and this is our final. Our initial speed is going to be what we had as our final speed for the first part of the motion there, which was this for the smooth surface. So now this one is going to be half. The object's mass is 50. The final one is the one that we don't know. The final speed minus the initial speed. So minus the initial kinetic energy. So this one is going to be the answer that we've calculated before, which was 7.67 u squared. So people, there you have everything there, right? So my best advice is that punch this on the calculator, all of it, right? And then after that, punch this on the calculator here, you'll get 25 VF squared. And then you'll also have your answer here. That answer that you get here, transpose it to the right, and then now you will get your answer. You should get that your answer for the VF, if everything you did here correctly, you should get that your answer for VF, it should be 10.05 meters per second. But everything should be done correctly there. This is going to result into this answer. So let's just check. It's 50 times 9 times 9.8 times 5. The cos of 90 minus 30 plus 33,95 times 5 cos 180. And then you add it with the answer you got from this side. So the answer here is 1055,25. Then the answer from this side is divide and then square root. So you're just going to transpose, and then yes, it will lead you to that answer. So if you do your maths properly, people, I think it's perfectly fine with this video. I'm just gonna end it here. So thank you very much, people. Unfortunately, we couldn't have this lesson live. It was going to be nice if it was interactive, if we interact and then we discuss together. But I hope when you watch here, you learned a lot of things, and then if it happens that you forget something, you will always go back and look at it again. Bye bye.